Artificial intelligence has gone from science fiction to reality. ChatGPT, Tesla's self-driving cars, medical diagnosis systems. These aren't fantasies anymore. They're here. But how do they work? What's actually happening behind the scenes? Most people think AI is magic, a black box that somehow thinks like humans. But it's not magic. It's logic, strategy, mathematics applied to decision-making. Stuart Russell and Peter Norvig wrote the definitive textbook on AI, the book that's taught in universities worldwide. It's called Artificial Intelligence, a Modern Approach, and it reveals the blueprint behind every intelligent system you interact with. In this video, we're going to break down the entire foundation of AI, revealing how machines actually learn, decide, and act. By the end, you'll understand not just what AI does, but why it works the way it does. And more importantly, you'll see why the future of intelligence, human and artificial, depends on understanding these principles. Dive in. What is artificial intelligence? The definition problem. Here's where most explanations fail. They define AI as making machines think like humans. But that's backwards. AI isn't about copying human brains. It's about creating systems that act intelligently, regardless of how they do it. Russell and Norvig define AI through 4 lenses. First, thinking humanly. This approach tries to replicate human cognition. How do humans think? How do we solve problems? If we can map the human mind, we can build it into machines. This sounds intuitive, but it's actually the hardest approach. We still don't fully understand human thought. Second, thinking rationally. This is different. Instead of copying how humans think, we ask, what's the optimal way to think? What's the logical, rational approach to any problem? This is where formal logic comes in. If we can express a problem logically, we can solve it mechanically. Third, acting humanly. The Turing test. If a machine can fool a human into thinking it's human through conversation, is it intelligent? This approach focuses on behavior, not internal mechanisms. Can it pass as human? If yes, call it intelligent. Fourth, acting rationally. This is the modern approach. We don't care if it thinks like a human or acts like a human. We only care if it achieves its goals effectively. A chess engine doesn't think like a grandmaster, but it makes better moves. That's intelligent behavior. The textbook focuses primarily on rational agents, systems designed to perceive their environment, make decisions, and take actions to maximize their success. What makes something an agent? An agent is anything that perceives and acts. A thermostat is an agent. A chess player is an agent. ChatGPT is an agent. The core principle is the same. Perception leads to action. Action changes the environment. New perception follows. A rational agent does one thing. It maximizes expected utility. Given what it knows and what it wants to achieve, it picks the action most likely to succeed. That's it. Everything else follows from that principle. How agents perceive the world. The problem of knowledge. Before an agent can act intelligently, it needs to understand its environment. This is harder than it sounds. How does a self-driving car know what's around it? How does a medical AI diagnose diseases from patient data? Sensors and perception. The agent starts with sensors. A camera, a microphone, patient records. These sensors deliver raw data, pixels, sound waves, numbers. But raw data is useless. A camera sees millions of pixels. A human sees a car, a pedestrian, a stop sign. The bridge between raw data and meaningful understanding is perception. The agent must convert sensory input into a usable representation of the world. In the early days of AI, this was done through handcrafted rules. If the pixel is red and circular, it's a stop sign. But this breaks instantly. What if it's raining? What if it's at an angle? What if the light is different? That's why modern AI uses learning. The agent sees thousands of examples of stop signs from different angles, in different lighting, different conditions. A neural network finds the pattern, not through explicit rules, but through statistical learning. The agent learns what makes a stop sign without being explicitly told. Representation. How you represent the world determines what your agent can do. Represent a chess position as a grid? Your agent can think in spatial terms. Represent it as a list of pieces and coordinates? Your agent thinks relationally. The representation shapes the thinking. This is crucial. The same problem represented differently leads to completely different solutions. A maze is trivial if you represent it as a graph with nodes and edges. It's nearly impossible if you represent each square individually. Russell and Norvig emphasize this repeatedly. How you model reality determines what your AI can accomplish. Dealing with uncertainty. Here's the uncomfortable truth. Agents rarely have complete information. A doctor doesn't have perfect knowledge of what's happening inside a patient. A self-driving car can't see around corners. A business can't predict the future. So, how do rational agents act with incomplete information? Probability. The entire modern AI approach rests on probability theory. An agent doesn't think, "This patient has disease X." It thinks, "Given the symptoms I observe, there's a 78% chance they have disease X, 15% chance of Y, 7% chance of Z." This probability comes from experience or data. When doctors train an AI diagnostic system, they feed it thousands of cases. The AI learns the statistical relationship between symptoms and diseases, not through memorization, but through understanding the probabilistic patterns in the data. This is why modern AI is so powerful and so limited. It's not certain, it's probabilistic. It makes the best guess given incomplete information, just like humans do. In fact, humans are terrible at probability. We're overconfident, biased, prone to errors. AI, when built correctly, is more honest about uncertainty. Problem-solving and search. The nature of goals. An agent doesn't just perceive, it wants things. It has goals. A chess engine wants to win. A medical AI wants to diagnose correctly. A robot wants to reach the goal location. But how does an agent go from, "I want this," to, "I should do this"? Through search. Imagine a robot in a maze. It wants to reach the exit. The robot doesn't understand walls or paths intuitively. It represents the maze as a state space, a set of all possible positions it could be in. From each state, certain actions are possible. Move forward, turn left, turn right. Each action leads to a new state. The robot's job is to find a sequence of actions that leads from its current state to the goal state. Uninformed search. The simplest approach? Try everything. Depth-first search goes deep into one path. Breadth-first search explores all nearby possibilities first. Both work, but they're inefficient. If the maze has 100,000 possible positions, you might waste time exploring dead ends. This is like wandering blindly through the maze. You'll eventually escape, but it takes forever. Informed search. Better approach, use information. The robot has a map. It can estimate which direction the exit is. Some moves bring it closer to the goal, some move it away. Algorithms like A* use heuristics, educated guesses about which path is most promising. Instead of exploring every possibility, the agent focuses effort on paths that seem to lead toward the goal. This is the difference between blindly trying every possibility and intelligently narrowing down to the most promising paths. The curse of complexity. Here's where theory crashes into reality. The search space explodes. Chess has about 10 to the power of 120 possible positions. A computer can't evaluate all of them. So chess engines use heuristics. They evaluate positions locally, look ahead a few moves, use pattern recognition. They don't solve chess perfectly. They search smartly. This is true for every real problem. The universe of possibilities is too large, so intelligent systems use heuristics, approximations, and limited look-ahead to find good solutions quickly, even if not optimal. This is a humbling truth. Perfect rationality is impossible. Rational agents do the best they can within computational limits. This isn't a bug in AI, it's a feature. It's how humans actually work, too. Knowledge and reasoning. Representing knowledge. Some problems aren't about search, they're about reasoning. A doctor looking at test results doesn't search through all possibilities. They reason from knowledge. If the patient has high fever and positive blood culture, they likely have sepsis. Sepsis requires immediate antibiotics. This is reasoning from knowledge, not searching through possibilities. How do we build AI systems that can reason like this? The first approach, formal logic. Represent all knowledge as logical statements. All patients with fever and positive blood culture have sepsis. This patient has fever. This patient has positive blood culture. Therefore, this patient has sepsis. This works. It's mathematically sound, but it fails spectacularly in the real world. Real knowledge is messy, fuzzy, probabilistic. Not all high fever, positive culture patients have sepsis. Most do, but exceptions exist. And in medicine, exceptions matter. Bayesian networks. Enter Bayesian networks. This is where modern AI separates from classical logic. A Bayesian network is a graph showing relationships between variables. Fever might cause chills. Sepsis causes fever. Chills might indicate sepsis. The network shows these connections, and more importantly, the probabilities. If I observe fever and chills, what's the probability of sepsis? The network calculates it by combining all relevant probabilities. It's reasoning under uncertainty. This is closer to how humans actually think. A doctor sees symptoms and updates their belief about what's happening. The patient probably has the flu, but sepsis is possible. The doctor assigns probabilities, not certainties. Bayesian reasoning, updating beliefs based on evidence, is the foundation of modern AI. From medical diagnosis to spam filtering, this principle applies. The AI starts with a prior belief. It observes evidence. It updates its belief. With enough evidence, the belief becomes very high or very low. The limits of reasoning. Here's the critical insight. Reasoning alone isn't enough. A doctor with perfect logical knowledge but no experience is useless. A medical AI trained on millions of cases but with no logical framework for reasoning is also limited. The best systems combine both: knowledge structures that let reasoning happen and learning mechanisms that improve from experience. This is why the most powerful modern AIs are hybrid. They use structured knowledge, They use learned patterns. They reason both deductively, from rules, and inductively, from data. Learning from data. The shift to machine learning. For decades, AI researchers tried to build intelligent systems by hand-coding knowledge. They'd write rules. They'd encode expert knowledge. It worked for narrow domains: chess, checkers, simple games. But it failed at everything else. Real-world problems have too much variation, too much complexity. You can't hand-code rules for every scenario. Then came data. The internet created massive datasets. Computing power increased. Storage became cheap. Suddenly, machines could learn from examples instead of being told what to do. This shift from knowledge engineering to machine learning is the biggest change in AI in the last 20 years. How learning works. The principle is simple. Show the machine examples. Let it find patterns. Use those patterns to make predictions. A medical AI sees 10,000 patient records, symptoms, test results, diagnoses. The AI finds correlations. Certain combinations of symptoms tend to appear together. Certain test results correlate with specific diseases. Without being explicitly told, the AI learns the patterns. But here's the catch. The AI finds correlations, not causes. It doesn't understand why certain symptoms indicate a disease. It just learns that when these inputs appear, this output usually follows. This is why machine learning is powerful but limited. It works incredibly well at pattern recognition, but it can't explain why. A doctor can say, sepsis causes high fever because inflammation from infection triggers the hypothalamus. A medical AI can't. It just learned that high fever correlates with sepsis. Types of learning. Supervised learning. The agent learns from labeled examples. Here's a picture of a cat. That's the label. Here's a picture of a dog. That's the label. The agent learns to distinguish them. Almost all successful modern AI uses supervised learning. ImageNet, GPT models, recommendation systems, all trained on labeled data. Unsupervised learning. The agent sees data without labels and finds patterns on its own. Here are 1 million customer purchases. Group them by similarity. The AI might discover that certain products are frequently bought together, even though nobody told it to find that pattern. Reinforcement learning. The agent acts, observes consequences, and learns which actions lead to rewards. A chess AI plays millions of games. It learns which moves typically lead to victory. No labels needed, just feedback about outcomes. The role of neural networks. Neural networks are the dominant learning architecture today. They're inspired by biological brains, but operate quite differently. A neural network is a web of interconnected nodes. Each node takes inputs, applies weights, and produces an output. By adjusting the weights based on error, the network learns to transform inputs into desired outputs. The magic is in the scale. A simple network might have thousands of nodes. Modern AI systems have billions. With so many parameters to adjust, the network can learn incredibly complex patterns. But this creates a problem: the black box. A neural network with a billion parameters is essentially uninterpretable. You feed in data, it gives output, but you can't easily explain why. Its learned patterns too complex for humans to articulate. This works great for image recognition. It's problematic for medical decisions or loan approvals, where explainability matters. Overfitting, the fundamental problem. Here's a pitfall every AI system faces: memorization versus generalization. A neural network can memorize training data perfectly. Feed it 10,000 examples of cats and dogs. It learns to classify them with 100% accuracy. But show it a cat from a slightly different angle, in different lighting, a breed it hasn't seen. It fails. The network didn't learn what is a cat, it memorized these exact pixel patterns are cats. It overfit. Good AI systems generalize. They find underlying patterns that work on new, unseen data. This requires careful design. Not too simple, underfitting. Not too complex, overfitting. And large, diverse training data. Planning and decision-making. From reactive to deliberative. A simple agent reacts to its environment. See obstacle, turn. See food, eat. See threat, run. But complex goals require planning. A robot needs to reach a location on the other side of the city. It can't just wander. It needs a plan. A plan is a sequence of actions expected to achieve the goal. The robot maps the city, considers different routes, picks the best one, then executes. This requires the agent to think ahead, to imagine future states, to reason about whether a plan will work before executing it. The planning problem. The fundamental planning problem. Given an initial state, a goal state, and a set of possible actions, find a sequence of actions that transforms the initial state into the goal state. Sounds simple. In practice, it's incredibly complex. Why? Because the world is dynamic. The robot plans a route, but during execution, a road is closed. A new obstacle appears. The plan becomes invalid. Good planning systems handle this through replanning. Execute the plan step by step. If the world changes unexpectedly, replan. Modern robots do this constantly. They execute a few moves, check the environment, replan if needed. Decision theory and utility. But some decisions don't have a clear path to a goal. A doctor decides between two treatments. Both could work. Both have risks. How does a rational agent choose? Through expected utility. Each action has an expected outcome and a probability. The action with the highest expected utility is best. Treatment A. 80% chance of cure with minor side effects, 20% chance of failure. Treatment B. 60% chance of cure with major side effects, 40% chance of failure. Expected utility depends on how much we value cure versus avoiding side effects. Different patients value these differently. That's why rational decision-making requires understanding preferences, not just probabilities. This is crucial for AI in human domains. An AI making medical decisions needs to understand patient preferences. An AI allocating resources needs to understand organizational values. Rationality isn't objective. It's defined by what the agent values. Markov decision processes. For sequential decisions over time, Russell and Norvig introduce Markov decision processes, MDPs. An MDP models a series of states, actions, transitions, and rewards. At each state, the agent chooses an action. The action leads to a new state, probabilistically since the world is uncertain. The agent receives a reward. Then it chooses the next action. The goal: find a policy, a mapping from states to actions that maximizes total reward over time. This framework applies everywhere. A robot navigating a building, an autonomous vehicle on the highway, a recommendation system deciding what to show you. All are solving MDPs. The key insight: the agent must balance short-term and long-term gains. Eating immediately gets food now. Hunting gets more food later. A good policy balances immediate and future rewards. Advanced topics. Natural language processing. Humans communicate through language. For AI to interact with humans, it must understand language. But language is ambiguous, context-dependent, and filled with nuance. Russell and Norvig cover the foundations: parsing, understanding sentence structure; semantic analysis, understanding meaning; and pragmatics, understanding intent. Modern large language models like ChatGPT approach this differently, through massive scale and statistical learning rather than explicit rules. But the underlying challenges remain. Language understanding is still unsolved. Computer vision. Seeing is understanding. For AI to navigate the world, it must interpret visual information. Early computer vision tried explicit rules: find edges, identify shapes, recognize objects. It was brittle. Modern computer vision uses deep learning. Convolutional neural networks learn to extract features from images automatically. They don't care about edges or shapes. They learn whatever features best predict the task. This has enabled self-driving cars, medical imaging, face recognition. But it's also revealed the limitations. These systems can be fooled by adversarial examples, inputs specifically designed to cause misclassification that humans would never mistake. Robotics. A robot must perceive, reason, plan, and act in the physical world. It's AI applied to embodied agents. The challenges are multiplied. The world is continuous, not discrete. Uncertainty is high. Action effects are imperfect. A robot commanded to move forward might slip. Sensors are noisy. Good robotics integrates all components of AI: perception to understand the world, reasoning to plan, learning to improve, control to execute actions smoothly. Multi-agent systems. Finally, what when multiple agents interact? A game with two players, a negotiation between two companies, an autonomous vehicle sharing the road with others. Now rationality becomes complex. My best action depends on what you do. What you do depends on what I do. It's a recursive problem. Game theory provides the framework. Rational agents in multi-agent settings reach equilibrium, a state where no agent can improve by unilaterally changing strategy. This has implications for AI safety. As AI systems become more powerful and autonomous, multi-agent scenarios become more common. Understanding how multiple agents interact, potentially with conflicting goals, is critical. The frontier: AI safety and challenges. The alignment problem. Russell and Norvig don't explicitly frame it as such, but the entire textbook points toward one critical problem. How do we ensure AI systems do what we actually want? It's easy to specify a goal in abstract terms: maximize profits, or win the chess game. But in practice, goals are complex and context-dependent. A robot told to clean the house efficiently might remove all furniture to reduce cleaning time. A system told to maximize engagement might addict users. A recommendation algorithm told to increase clicks might spread misinformation. The goal seems clear until you deploy it. Then unintended consequences emerge. This is the alignment problem. How do we specify what we actually want in a way that's complete, accurate, and robust to misinterpretation? Scalable learning. Current AI systems learn from data, but data reflects human choices and biases. Biased training data produces biased systems. Incomplete data produces incomplete understanding. As AI becomes more powerful, the consequences of biases and incompleteness scale up. A biased medical AI affects thousands of patients. A biased hiring algorithm affects thousands of job seekers. How do we build learning systems that are fair, accurate, and robust? This remains an open problem. The limits of current AI. Finally, the textbook constantly reminds us, current AI systems are narrow. They solve specific problems through pattern recognition and search. They don't have common sense. They don't transfer knowledge across domains. They can't reason about novel situations. A chess AI that beats all humans has no idea what a chess piece is. A medical AI that diagnoses disease can't tie its own shoes. Intelligence remains fragmented. Creating artificial general intelligence, AI that matches human flexibility, creativity, and adaptability, remains an unsolved problem. The techniques in this textbook are powerful but limited. Russell and Norvig's textbook is over 1,000 pages. It covers decades of research. But the core message is simple. Intelligence is the art of making good decisions with incomplete information. Rational agents perceive their environment, update their beliefs when they encounter evidence, reason about consequences, plan to achieve goals, and learn from experience. These principles apply to humans and machines. They apply to simple systems and complex ones. They apply to games, medicine, robotics, and business. The textbook doesn't promise that AI will be perfect. It shows that AI follows principles, and those principles can be understood, analyzed, and improved. We're living in an age where these principles are being applied at massive scale. Understanding them, really understanding them, is crucial. Not just for researchers and engineers, but for anyone who needs to make decisions about AI or lives in a world shaped by it. The future of intelligence, human and artificial, depends on getting these principles right.